the tensor T was going to be sent by P through its eigenscheme, and this was the map. So, no, sorry, to the section associated with it. And what I wanted to show is that the kernel of this map was exactly equal to 0 if the degree of a polynomial was odd, and q to power b over 2 if my b was even. So yeah, it's not the first one to b to so the idea here is to use the composition of the sim D of B into irreducible SOP modules. And so you have that the sim D of B is equal to the direct sum of H B minus 2J, where this H B minus 2J is equal to the T, so we can use F times Q power J, such that this F is a harmonic polynomial. Of the degree B minus 2J. So now we have the composition of our symmetric space into irreducible SOP modules. So what we can do now is to utilize Schur lemma in each of these blocks. And Schur lemma is really good because you can just compute it at one point and see if this map is 0 or not. So we can compute the P over the point x0 plus xi to power d minus j and qj. And we can see that this map of this is different from 0 every time that this part appears. And when this part does not appear, it's exactly when we have which is 0 that is generated by q of our b over 2. And in this case, when you apply phi, you get that well, phi is going to essentially send to that matrix that is the gradient of phi and x. So here is going to be the gradient of q computed as x, and one can see that this matrix is going to be of rank 1 every time. So this means that for our context, this is a 0 for this map. And in all the other cases, for J here, when it's different from 0, you get an image that's non-zero. So this implies that this map has the kernel 0 if the degree is odd, because it does not appear in the decomposition, and if it is even, it appears. So maybe so I tried not to use the blackboard anymore. Okay. That's too difficult.
Still have 20 minutes.
Okay.
19.
And the second part, so this part here that I just explained completely describes the part of phi, the map phi. So we need to understand what is happening with the map C. So we have this lemma that says that if you have two polynomials such that the 0 locus of its global sections are the same, then they can only differ by multiplication by scalar. That in the projective context mean that they are the same. And for this part, it's much more technical. The idea is to show that the H0 of the endomorphism of the bundle E is isomorphic to the isomorph to the H0 of the ideal shift of C of P, the eigenschema, tensor the P. And what this will mean is that whenever you have that the zero locus are the same of those sections, it means that it exists endomorphism that takes S of F through S of G. And now, in this case, it's much simpler because our bundle E is actually just the pullback of the quotient bundle. So it's a simple bundle. And the endomorphism of it is equal to the complex numbers. So you obtain this for free. That is just a multiplication by scalar. And if we put these two results together, we obtain the main theorem that generalizes the first two results to polynomials of any number of variables. So we obtain exactly the same behavior. We have that the fibers of this map is just the polynomial f if the degree is odd. Otherwise, it is f plus the quadratic form that I wrote before here, to power d over 2 when this is even. And now we wanted to actually generalize this for partially symmetric tensors. And the idea is all the same. I will not write, but the idea is, again, I take this, divide into take the decomposition SLV modules, then the tensor product of all of those is a SOV1, Cartesian, SOV2, so on, irreducible module, and apply Schur lemma. And the second part is, again, it's the same thing. The way that you prove this isomorphism is really long here, and you need a lot of you need to control some cohomologies. That is difficult. And here is where this boundary format condition appears. So those cohomologies that you have to control to show the isomorphism between these and the H0 of the endomorphism, it only happens the vanishings when this boundary format condition appears. And although it has a geometrical meaning, it is not clear how it is playing here, how to relate the existence of the hyperdeterminant and so on to try to get rid of this. And but you get the same. You get that if you have the two tensors, that the sections associated to them have the same zero locus, you have a map. You have that they can only differ by multiplication by scalar. And the last condition is again technical. It's just if the k is equal to 2, you cannot allow the matrix case that you saw before that was much different from tensors. And this is the main result of all the work I did. That is that in the general case, if you assume the boundary format condition, if we're not in the matrix case, you have that the fiber of this map is just a T. If you have that all the degrees are odd, and if it all the if some degrees is odd, and it is again just the sum of the product of the quadratic forms if all the degrees are even. Because again, the only way that this guy appears is if you have all H0s appearing everywhere. So these close the first part of the talk, and then I want to talk a bit just about this boundary format condition. So there's some problems that this boundary format condition has been an obstruction. One of them is, does T belong to the linear span of its singular tuples, of its eigentensors? And this is a good question because for matrices, the singular pairs, they give a minimal decomposition of the matrix. For tensors, again, this is answered when the boundary format condition is satisfied, and you have that T belongs to that, and it means that the T is a linear combination of its eigentensors. However, the difference between matrix and the tensors is that this decomposition is not minimal in general. So unfortunately, it's not so good as the matrix one. The second question is, what is the dimension of Z of T? And the last question is, are tensors determined by their singular vector tuples? So to tackle these first two questions, this space was defined first by Ottaviani and Paulette, and then later it was utilized by Dreisma and Ottaviani and Tocino. So these critical space, essentially these are the minors of that matrix that I showed before, that you have the flattening of the tensor and the vector itself, the rank one that we are using. And the difference now is just that we're allowing higher rank solutions. So before we were looking just for solutions of rank 1, here we have any rank, and this define a linear space. And Dreisma, Ottaviani, and Tocino in 2015 have proven that together with again the boundary format condition, Z of T and the linear span is exactly equal to this critical space. And they computed exactly what was the dimension of this critical space. In particular, they showed that the T belongs to the critical space. And so immediately you get that the T is in the linear span of its singular vector tuples. So this year, together with Luca Sodomaco, we try to start to analyze what happens when this boundary format condition is removed. So the first case is the format 2 to 4. And what they found is that a different behavior already happens. We have that Z of T has dimension 6. So, and the critical space here has dimension 7. So we have a codimension 1 now. So we found that this new equation that is satisfied by the sum of the linear singular vector tuples is given by this sum of determinants. And one can verify that just by substituting this first row by T again, these two determinants are 0. So what this means is that the tensor is satisfying also the extra equation that the Z of T satisfies. So it means that even though there is a dimension 1 in this space, the tensor is still in this smaller space that is just based on of the singular vector tuples. So unfortunately, this was just in Macaulay. We don't have yet a geometrical explanation of what this is happening, what's happening here, how it's coming. And again, we tested for another 2 cases. That was 2, 3, 5. And in this case, we have codimension 2. And we found this new 2 equations satisfied by the singular vector tuples. And those 2 equations are again satisfied by the tensor itself. So you have again the membership problem being, it holds even though you have a higher codimension. And this was the last case that the computer could handle. That was 2, 3, 6, where we found 3 equations, new equations. And again, the tensor itself satisfies those equations. So you have, again, the membership problem works. And also we computed the dimension because we can control the dimension more or less utilizing the cohomology techniques that I said before. But it's difficult because they don't vanish anymore, all of them. So it becomes very complicated. And the last case that we looked at, it was this format. So every dimension 2 except the last one that is L plus 2. Here we have L2. So this is the first case beyond the boundary format for this format. And it was something really surprising because we expect that there would be always a codimension between the linear span of the singular vector tuples and the critical space. But in this case, we found that this dimension coincides with the dimension of the critical space exactly when the L is bigger or equal to 4. And so this was really good news because what this implies is immediately that the membership problem was solved because the tensor itself is going to lie here. And well, this was utilizing the technique of Dreisma, Ottaviani, and Tocino. It's the same technique, just we don't have the vanishings anymore. So you need to analyze some maps in the causal complex to try to understand what are the kernels, what is happening exactly. So it's not a really good technique in this case because it's really difficult. So it's really difficult to generalize for higher formats. And well, then what I obtained was that in those three cases that I mentioned, we have the membership problem solved. We have that P still beyond the boundary format is in the span of the singular vector tuples. And utilizing this fact, we gave a proof that again tensors are determined by its singular vector tuples. And this is a really nice proof because it does not utilize anything else than the membership problem. So if you want to solve the membership problem, this is already solved. It is a proof that only relies on that fact. And yes, that was everything that I had to say. Thank you a lot. And those are the two papers if anyone is interested.
Many thanks.
Put the definition of the critical space up one more time. So why is it linear? It looks like, yeah, because you are considering the unknowns to be this ZPI, so they are linear. These are the entries of the tensor, and those are the fixed. These fixed, and these are the variables. The critical space is of a fixed tensor field.
When you say for general tensor, they are determined tensor. General means in fact it's not true in general, but it's true for tensor except some
yeah, except some
hypersurface.
exactly.
So do you know what is this hypersurface? Do you have a
I don't
kind of discriminant?
I don't know if there is a classification because, for example, a decode tensor is maybe not general enough, but behave well.
So the hypersurface,
Yeah,
when
the
the zeros are no more defined,
Or
it's called the EV discriminant.
so
It's
is it-
harder to be computed in general.
Yes.
It's harder to be computed. But even for a matrix, no, it's a sum of squares, but it's the discriminant of the characteristic polynomial. For a matrix, it's really this.
and for tensor and
Well, so in this eigen case, there's some results. So this special case is called eigen discriminant, and some results about the degree and this small case.
Other questions? From remote participants, maybe, if they can hear us. If not, thanks again.